Hello, students. Today we'll discuss the next topic, that is deadlocks. Deadlocks is nothing but whenever a process requests the resource and other process requests the same resource in a cyclic form. Whenever a process, if it is request the other process will request the other process, is called as deadlock. First, we'll see the definition. Deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource acquired by some other process. Therefore, set of processes are there. Therefore, it will be blocked, and each process is holding a resource and waiting for another resource acquired by some other process. We can see the example, that is when two trains are coming towards each other on the same track and there is only one track. None of the trains can move once they are in front of each other. On the same track, whenever two trains are coming, therefore this train will not go that side, that train will not come this side. Therefore, it is a deadlock situation where the train cannot move at all. That we can see in a picture format. Examples for deadlock. Now this is the picture. You can see two trains are in opposite direction. Therefore, none of the train can go on either side. Therefore, it is a deadlock situation. The second example, you can see the cars which are in green color as well as in red color. The green color cars are coming forward and the red color cars are blocked. Therefore, these cars are cannot go on that side, and those cars cannot move forward. Therefore, that is a deadlock situation. And third one is whenever a door is opened, therefore we can see the door is open, there I cannot actually lock the door. Therefore, it is a deadlock situation. Next, we have system model. A system consists of a finite number of resources to be distributed among a number of competing processes. The first point, if a system has two CPUs, then the resource type CPU has two instances. Similarly, the resource type printer may have 5 instances. We have a single instance as well as multiple instances in a system. One CPU, if it is there, the request will be sent either from the IO device, keyboard, or from mouse. Therefore, only one instance will be there. More number of printers, if it is there, or more number of CPUs that are there, multiple instances can be requested for the process to be completed. We have three, whatever the points in this system model. First one is request, second one is use, third one is release. The process requests the resource. The request cannot be granted immediately. Then the requesting process must wait until it can acquire the resource. Use, the process can operate on the resource. And release, the process releases the resource. If a print has to be given, then from CPU or from the keyboard, the operating system will manage in between. I'll be giving as control P, or directly from the option will go as print. Therefore, directly it will be connected, software will be there, request will be done from the user through the keyboard, then the process will be done in between, then it will be released, that is, it has been printed and it is printed, and the process is completed. Deadlock in system model. How the deadlock will occur in the system model. To illustrate a deadlock state, consider a system with three CD rewritable drives. Suppose each of three processes holds one of these CD rewritable drives. If each process now requests another drive, the three processes will be in a deadlocked state. Therefore, three CDs are there. Therefore, if I am giving only one whatever with the request to three of the whatever with the drives, therefore, which one it has to open, it cannot be taken. Therefore, it is a a deadlock situation. That you can observe in the normal PC, that is we call as system model. Next, we go to the next topic, that is deadlock characterization. In that, we have two what are within points that are there: necessary conditions, and second one is resource allocation graph. First, we'll see the necessary condition. A deadlock situation can arise if the following four conditions hold simultaneously in a system. First one is mutual exclusion, hold and wait, no preemption, and circular wait. Mutual exclusion. At least one resource must be held in a non-shareable mode. That is, only one process at a time can use this resource. If another process requests that resource, the requesting process must be delayed until the resource has been released. Hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. Mutual exclusion, one if it is complete, then only it goes to the, if another process requests the resource, the requesting process must be delayed until the resource has been released. Therefore, first process must be completed, then only it goes to the next, whatever the process to be accepted. Hold and wait. At least one resource and waiting to acquire additional resources that are currently being held by other processes. Therefore, you have to wait for that other process to be completed, then it will be continued. Resources cannot be preempted. That is, resource can be released only voluntarily by the process holding it after the process has completed its task. Preemption is nothing but you will not have any uh, backward. Therefore, once the process is completed, then it cannot go back. Therefore, it has to complete it. Circular wait we have. We have P0, P1, P2 up to Pn. We will take the processes. Waiting process must exist such that P0 is waiting for a resource held by P1. P1 is waiting for a resource held by P2, and so on. Is waiting for a resource held by Pn. Pn is waiting for a resource held by P0. Therefore, it is a circular process. Set of processes will be there. P0 is waiting for P1, P1 is waiting for P2, and so on up to Pn. Now, these are the different conditions that are there where a deadlock situation can arise. Next, we will go to the resource allocation graph. That is, the resource allocation graph is the pictorial representation of the state of a system. As its name suggests, the resource allocation graph is the complete information about all the processes which are holding some resources or waiting for some resources. Now, here in the resource allocation graph, the pictorial representation of the entire deadlock situation can be done in a graphical method. It also contains the information about all instances of all the resources, whether they are available or being used by the processes. In resource allocation graph, the process is represented by a circle while the resource is represented by a rectangle. Resource allocation graph is actually a directed graph where we have arrows that will be depicted. Therefore, process will be represented in the form of a circle, and the resource will be represented in the form of a rectangle. Resource allocation graph, we have vertices as well as edges will be there. Vertices consist of, we have two, that is process vertex, resource vertex. Now, in this, every process will be represented as a process vertex. Generally, the process will be represented with a circle. Then second one, we have resource vertex, where CPU process will be there, that is print. Therefore, it will be requested from the CPU, that is maybe through keyboard, uh, that is a process. Therefore, every resource will be represented as a resource vertex. We have two types will be there: single instance type, multi resource instance type. It represented as a box. Inside the box there will be one dot, so the number of dots indicate how many instances. Here you can see the vertices. We have process vertex, resource vertex, where single instance one dot is there, that is CPU. Multiple instances, that is we have registers. Therefore, so many number of registers that are there in the CPU. I have two types of edges are there, that is assign edge as well as request edge. If you already assign a resource to a process, then it is called as assign edge, and request edge is nothing but it means in future the process might want some resource to complete the execution, that is called as request edge. Now here you can see the request that is going to the process, and from the process the request is been done. Therefore, it is assign edge as well as request edge. Now if you can see the example for resource allocation graph, here the P1 and P2 are the processes, as well as R1 and R2 is called as the resources. Here we are taking a single instance resource type with a deadlock situation. Whenever if it is in a cyclic process, that is P1 to R2, and from for R2 to P2 and P2 to R1, again R1 to P1. Now this is a cyclic form, therefore it is a deadlock situation. If this is a cycle in the resource allocation graph and each resource in the cycle provides only one instance, then the processes will be in a deadlock. You can see the example here. The process P1 holds resource 1. Process P1 holds resource 1, and process P2 holds resource R2, and process P1 is waiting for R2, and process P2 is waiting for R1. In the process P1 and P2 will be in a deadlock situation. Therefore, P1 and P2 are the two processes requesting for R1 and R2 are the resources. This is a single instance resource type is in a deadlock situation. Now, single instance, the same whatever the example that we can take for the single instance without deadlock, where R1 and R2 are the resources, and we are taking a directed graph with P1, P2, and P3. Three processes are there. Therefore, P1 is holding R1, and P2 is holding R2, and P3 is waiting for R1, and P3 is waiting for R2. Here is an example that you can see. It shows the processes P1 and P2 acquiring the resources R1 and R2, while process P3 is waiting to acquire both resources. In the example, there is no deadlock because there is no circular dependency. In the previous example, whatever we have seen, a cyclic form it is there, where P1 to R1 and R1 to P2 and P2 to R2. Therefore, the cyclic form it is there. Therefore, it is a deadlock situation. Here we are actually, it is not a cyclic form. Therefore, it is a no deadlock, but it is a single instance we have taken because it is there only one dot inside the rectangle. So, cycle in single instance resource type is the sufficient condition for deadlock. Now, methods for handling deadlocks. We can use a protocol to prevent or avoid deadlocks, ensuring that the system will never enter a deadlocked state. Protocol is nothing but it is the rules and regulations that are given for avoiding deadlocks. Like we have a traffic signal is there, we have different signals that will be there on four sides. Therefore, one will be waiting, other will be going on other sides on the road. The same situation here, processes will has to wait for not to be in a deadlock state. We can allow the system to enter a deadlock state, detect it, and recover. We can ignore the problem altogether and pretend that deadlocks never occur in the system. To ensure that deadlocks never occur, the system can use either a deadlock prevention or a deadlock avoidance scheme. Now, deadlock prevention provides a set of methods to ensure that at least one of the necessary conditions cannot hold. Deadlock avoidance requires that the operating system be given additional information in advance concerning which resources a process will request and use during its lifetime. The process, whenever if it is in the deadlock state, it has to recover it, or it can be prevented, or it can be avoided. In these cases, the deadlock can be handled. Thank you.